Today we will start chapter 3, and for this chapter 3 we will start from 3.2 instead, which consists of uh, some parts. The first one is on division, polynomial division. Which consists of long division, and synthetic division. Okay, synthetic division is a division can only divide it by the form x minus c. Long division is more general division where a polynomial divided by another polynomial. Then another part here which are related are remainder theorem. Let's remind ourselves what is remainder theorem. Remainder theorem says the following. If polynomial px is divided by x minus c, then the remainder is remainder r is equal to pc. And you can see that we can use synthetic division for that. And the one related to consequence of remainder theorem is factor theorem. That says if px is a polynomial and pc, when you replace x by c, it's equals to 0, remainder is 0, okay, then x minus c is a factor of that polynomial px. Again, big warning, you need to watch that lesson 10 before you get into here. Okay, if you have not watched lesson 10, have not watched lesson 11, then what I do here may confuse you even further. Okay, because there are terminologies to understand, like what is a polynomial, okay, for example, and what is a zero, what is a factor, and so on and so forth. Okay, let's start. I will do these problems. How many problems here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. So 14 problems from this section. And if you have more problems you would like me to go over from this section, let me know. Okay. The hard part is really to explain what are those. So this is where the lesson 10 and lesson 11 becomes very, very crucial. You need to watch them first. Okay. This polynomial here, yes, a lot of terminologies that you need to memorize. Okay, let's start with number 3 in 3.2. The question is let fx equals to let fx equals to 3x cubed plus 2x minus 4. Okay, and px equals to 2x squared plus 1. What we want to do is find the quotient and remainder if fx divided by px. Now notice that the px is not in x minus c form. In fact, it's not degree of 1. Give me a second. Let me mute you. Now, because of that, then we need to do long division where the dividend is inside the house, 3x cubed plus 0x squared plus 2x minus 4. Okay, notice that I insert 0x squared as a placeholder. Okay, and in the outside, I have 2x squared plus 0x plus 1 also as a placeholder 0x. Now for the divisor, if you skip that 0x, it is okay. But for the dividend, the 0x squared here, you have to insert it. Okay. Otherwise, there could be confusion with because of the place. We need the placeholder basically. Okay. Now then we see 2x squared times what equals to 3x cubed. 2x squared times what equals to 3x cubed. So that will be 3 over 2x. Now think about that. 2 times what give us 3? 3 over 2. Right? X squared times what give us x cubed? That's why we need another x. Right? Okay, let's rebuild it. Let's rebuild it. Build that again. So 2x squared times what give us 3x cubed. Now 2 times 3 over 2 will give us 3. Okay, and x squared times another x give us x cubed. So 2x squared will be multiplied by 3 half x will give us 3x cubed. Now, long division is something we have learned in our Algebra 1 or at SMC, that's Math 31. After Math 31, then you do Math 20, and then you do geometry at the same time. Math 31, as I remember, or 32. Oh, Math 32, I mean geometry. And then you can get to pre-calculus. Okay, so long division is something we learned at least 1 year ago. Now, after we know we multiply by 3 half x, then you distribute that 3 of x to this guy and also to this guy. Okay, so that will be plus 0x squared plus 3 half x. Now, and then we subtract 3x cubed minus 3x cubed is 0. 0x squared minus 0x squared is also 0. How about 2x minus 3 half x? What about 2x minus 3 half x? That's 4 over 2x minus 3 half x, right? That's equals to 1 half x. So I get 1 half x here minus 4. Now we know we can stop the division if the degree of the remainder is already less than the degree of the divisor. The remainder is degree 1. The divisor is degree 2. Now from here, we know we can stop. Then we can summarize. We can summarize fx divided by px as instructed by the question, which is 3x cubed plus 2x minus 4 divided by 2x squared plus 1. When we divide that, we will get 3 half x plus the remainder 1 half x minus 4 over 2x squared plus 1. That's the quotient. Okay, that's the quotient. Now we can also say this is the quotient and this is the remainder. Cool. But overall, this is the quotient. Overall, this is the quotient. Now here we have some, how to say that, when we say quotient, which one it refers, Thomas? When you divide two polynomial, the quotient is this. This is the quotient. But then when they ask more specifically, what's the quotient, what's the remainder, then you say that this is the quotient and this is the remainder. Okay? I know it's a bit confusing at this point, you know, but the first quotient, the big quotient I'm talking about is basically just a regular number. If I have 7 divided by 4, what is the quotient 7 divided by 4? When you divide 7 by 5, divided by 4 is 1 and 3/4. That's the quotient. Okay, but when we try to separate, distinguish what's the quotient with the remainder, then we say this is the quotient. The quotient is 1. Okay, the remainder is 3. Okay, so see, even the first question already bring us to some confusion in terminology. Okay, but eventually you will get used to it. Eventually you will get used to it. From the context, you will know, oh, you know what, this is the quotient, and therefore the quotient is what, the remainder is what. Okay, number 7. Number 7. Fx equals to 10x plus 4 and px is 2x minus 5. Is that the next question I would like to do? Yeah, number 7. So when I divide fx divided by px, that is 10x plus 4 over 2x minus 5. That's divided. 10x plus 4 divided by 2x minus 5. We ask ourselves 2x times what equals to 10x. Now this one is easy. It's multiplied by 5, right? Okay, but the 5 is degree of 0, so I need to put that 5 above degree of 0, the constant on the long division. Okay, so I will get 10x minus 25. Then when I subtract, be very careful, we are subtracting here. So it's supposed to be 4 minus negative 25. Okay, that gives us 29. So what is the quotient? The quotient is 5 plus 29 over 2x minus 5. Okay. Now, to be more precise, to go even more detailed, then the quotient is 5 with remainder 29. That's for number 7. Number 9. Use remainder theorem to find FC. Fx equals to 3x cubed minus x squared minus 4. And we want to find what is F2. Now, of course, we have learned from chapter 2 to find F2. One way to find F2, the old way is you replace x by 2, right? That's 3 times 2 cubed minus 2 squared minus 4. Is it okay? That's how we did it before, right? Nothing really new. 3 times 8 minus 4 minus 4. That's 24 minus 4 minus 4. That's 16. Okay. Now, so what if we use remainder theorem, Thomas? Basically, when we divide that fx by x minus c. So 3x cubed minus x squared plus 0x minus 4. Okay, that's the fx, right? The polynomial. And we divide by x minus c. Okay, now whatever the remainder later on, that's the F2. That's what remainder theorem says. Okay, now let's start. X from that x minus 2 times what give us 3x cubed. Multiply by 3x squared, right? Okay, so I will multiply by 3x squared here. So 3x squared times x is 3x cubed minus 6x squared. And then when I subtract, I get negative x squared minus negative 6x squared. That's positive 5x squared. And then I bring the next term down. So we repeat the cycle again. Now x times what give us 5x squared. Multiply by 5x, right? So I multiply plus 5x, which I will distribute with that x minus 2. So I will get 5x squared minus 10x. Then I subtract again. Yeah, we keep on doing that until we cannot go further. Okay, so 0x minus negative 10x, that will give us 10x minus 4. Now we repeat the cycle again. X times what give us 10x. Oh, that's easy. That's multiplied by 10, right? Okay, so plus 10. That gives us 10x minus 20, which when we subtract, we get negative 4 minus negative 20. That's 16. Now that's the remainder, right? That's the remainder. So from there we say that F2 equals to 16. Oh, Thomas, that's a long way to compute F2. I will just use the original method. Yeah, if you need to use long division, then original method will be best. Okay, if you need to use long division, then yes, original method. F2, you just plug 2 into the function directly will be best. Okay, but there's a third method. Notice that we can rewrite if you F2 is the remainder when the polynomial fx is divided by x minus 2. Is right? Now, on the other hand, we know we can divide a polynomial using synthetic division if the divisor is x minus c. In other words, now I can divide that polynomial fx by x minus 2. I will write the 2 here. And then on the top row, so when you do synthetic division, you consist of 3 rows. This is the first row, the second row, and the third row. Okay, now the first row inside the box will be the coefficient of the divisor, the dividend. Okay, 3x cubed minus 1x squared plus 0x minus 4. That's the first row. And then we divide by x minus 2. So I put 2 here. Okay, whatever you divide by x minus c, then you put the c here. You can say that's the opposite of negative 2, and you put 2. Now then, synthetic division is done in the following way. The first number always fall down. You copy that. Okay, and then 3 times 2 give us 6. And then you add this. Okay, you always add the column. You always add the column. This is 5. Then 5 times 2 is 10. You add that again. You get 10. 10 times 2 is 20. You add that again. You get 16. Now, the last column on the last row, you always box that separately. Always box that separately. So you see that using synthetic division, let me move this a little bit to the left. Yeah, so using synthetic division, then we get that 3x cubed minus x squared minus 4, when you divide that by x minus 2, we see the quotient is 3x squared plus 5x plus 10. Now, this 3, 5, 10 comes from here. Okay, and the degree for that 3, the first number, is degree of 2, which is 1 degree less than the degree of the polynomial you divide by. Divide when the 1 degree of the polynomial you divide from. Degree of 3 becomes degree of 2, plus 16 over x minus 2. Okay, that's the quotient. But according to remainder theorem, then F2 equals to that 16. Now, synthetic division enables us to divide by x minus c form a lot faster, and that's where we can use for remainder theorem. Okay, so using that, let's try, for example, number 11. Number 11, fx equals to x to the fourth minus 6x squared plus 4x minus 8. And we want to find what is f negative 3. Now, I will just go directly with syntactic division. Okay, solution. Syntactic division consists of 3 rows. The first row consists of the coefficients of the polynomial we divide from, the coefficient of the dividend. Okay, start from degree of 4, the coefficient 1, degree of 3, coefficient 0, degree of 2, negative 6, degree of 1 is 4, and the constant, negative 8. Okay, now because we want to find f negative 3, it means we divide by x minus negative 3, which is x plus 3. We will divide by x plus 3. Okay, so what is the c here? The c will be negative 3. Okay, so the guy that you put here is the opposite of that guy. Okay, because we catch that x minus 3, right? This is x minus c. So the c is negative 3. Now, that implies this negative 3 will be the same to what we need there. Okay, now let's start the procedure. The first number falls down. 1 times negative 3 is negative 3. You add, you get negative 3. Negative 3 times negative 3 is 9. When you add this, you get 3. 3 times negative 3 is negative 9. When you add, that's negative 5. Negative 5 times negative 3 is 15. You add, you get 7. So you see that we are done with the division, right? So f negative 3 is equals to 7. Instead of plug in negative 3 into the polynomial, we use syntactic division to find f negative 3. In fact, we get something else. And the one day I asked what is f negative 3. Okay, but I want to point out that we get something else here. This is the same technique, the same procedure we will do if they had asked us to divide x to the fourth minus x 6x squared plus 4x minus 8 divided by x plus 3. If you divide that polynomial fx by x plus 3, then the quotient would have been 1 degree less from x to the fourth, right? That will be 1x cubed minus 3x squared plus 3x minus 5 plus the remainder 7 over x plus 3. Okay. I want to point out that this syntactic division is being used for 2 purposes. The first one is to find what is f negative 3, which is one of the outcomes if you actually divide it. Okay, so using that syntactic division, we get the quotient and the remainder. The remainder can be used to find that f negative 3. Okay, number 13. Then we go on, show that show that x plus 3 is a factor of fx equals to x cubed plus x squared minus 2x plus 12. Now, in the past, when we say x plus 3 is a factor of this polynomial, then you try to do factoring, right? Right now, no, we don't do factoring anymore. It's not a square, and I don't think we can do that by factorization by grouping, right? So how do we approach this question? Then we try to do it using factor theorem. So solution. Here's the idea. Here's the idea. If x plus 3 is a factor, maybe I write it instead of here, let me write it aside on the right hand side. So that you get the idea. If x minus 3 is a factor of that polynomial fx, then the remainder has to be 0. Right? Now, if the remainder is 0, then according to the remainder theorem, then f negative 3 is 0. Oh, by the way, according to our definition, it also means that negative 3 is a 0 of fx. Oh, so we have a terminology here. It's kind of strange terminology, even for me, first time I heard that, but I know 0 is a 0, right? But in polynomial, and actually for every function, we say C is a 0 of any function fx if fc equals 0. That's the definition of the word 0. Okay, but that's why when you write this 0, you cannot use number 0. No, don't use number 0. It's the word 0. Okay, a constant c is a 0 of a function if fc equals to 0. Okay, that's a definition though. Let me write it as a definition and I box it here. The first time you hear that, I know it sounds really strange. Okay, so to show that x minus 3, going back to this number 13, to show that x minus 3 is a factor, all I need to do is actually to show that when I divide by, when we say x plus 3 is a factor of this polynomial, all I need to do is to show when I divide by when I use synthetic division, dividing that polynomial by x plus 3, the remainder is 0. That's what I need. Okay, now coefficient of that polynomial, 1x cubed plus 1x squared minus 2x plus 12. Okay, now I need to show that the remainder will be 0. Okay, I need to show that the remainder is 0. But once we can show that the remainder is 0, then x plus 3 must be a factor. Okay, so I drop the first number down. 1 times negative 3 is negative 3. When I add, I get negative 2. Negative 2 times negative 3 is positive 6. When I add, I get 4. 4 times negative 3 is negative 12. When I add, I get 0. Okay, now since f negative 3 is equal to 0, then x plus 3 is a factor of that polynomial fx. Okay. In fact, let's say it this way. Basically, we are saying that x cubed plus x squared minus 2x plus 12 divided by x plus 3 is equal to x squared, 1x squared, right? 1x squared minus 2x plus 4 without remainder. Right? Now, because we don't have remainder, then that implies we can write that x cubed plus x squared minus 2x plus 12 as x plus 3 times x squared minus 2x plus 4. All of a sudden, we factor that polynomial. Okay. Now, there are a lot of details that you need to pay attention, but one of the key part that I need you to keep in mind to the point that I think I should box this. I think I should box this. Maybe I box that using this. Remember this diagram very, very well. Very, very helpful. Okay. Remember this diagram very, very well. First, if we say C is a 0 of a polynomial px, by definition, it means pc equals to 0. That is by definition for every function, not only for polynomial. Now, if pc equals to 0, then according to remainder theorem, to be more precise, factor theorem, okay, then x minus c is a factor of that polynomial. That's by factor theorem, remainder theorem. Okay. Now, later on, what is the purpose of we doing this? We know that if C is a real number, if C is a real number, then C comma 0 is an X intercept of the graph of Px. Okay, if C is a real number. So it's like you say one thing, it means three different things also. They come together. If C is a 0, then PC equals to 0, then x minus c is a factor of that polynomial. Okay, and you will see one way for us to graph px later on, and therefore we need to find the x-intercept. To find x-intercept of a polynomial, we need to find the zero of that polynomial. Now, to find the zero of a polynomial, we need to factor that polynomial. Okay, now from here also we have the side note of a side note. We have side note of a side note. And I need to emphasize this, and I hope you realize why I emphasized that in the past. Okay, the difference between a zero and x-intercept. Okay, a zero is just a number. C is a zero of a polynomial. Okay, C comma 0 is an x-intercept. Okay, let's do a side note for that and a small example for that. I know it can be confusing. If you don't follow me since the beginning, why I emphasize that x-intercept is a coordinate, x-intercept is a coordinate, then you may get very confused right now. Okay, let's say we have this. Well, let's say we have this, for example, a small example. Let's write it as a note. Okay, let's say we have let fx equals to x minus 1, x plus 2. Okay, now when we find the x-intercept, to find the x-intercept, notice we always do it this way. Okay, to find x-intercept, we set the fx equals to 0, right? I purposely factor this for you. Okay, then we say x equals to 1 and x equals to -2, right? Okay, at the time we solve it that way. And if you stop there, I will penalize you, remember? And I will still penalize you if you do that in your test 1. Okay, x-intercept are not numbers. The x-intercept of these functions are, the x-intercept of these functions are 1, 0, -2, 0. Those are the x-intercepts. So what is this x equals to 1 and x equals to -2? Those are the zeros. The zeros of fx, the zeros of fx are x equals 1, x equals -2. Okay, but those are not the x-intercept. The difference between zeros and x-intercepts, the zeros are just numbers. X-intercepts are coordinates. Okay, but Thomas, you know, it just means the same thing. No, they are not the same. Let me insist, the zeros are just numbers. X-intercepts are coordinates. Okay, but you know, all the zeros always becomes x-intercept. That's not true. That's not true. Okay, they are zeros of fx that are not x-intercepts. They are zeros of fx, they are not x-intercepts. Therefore, we cannot say that the zeros will be x-intercept. No, that's not true. Okay, let me show you the example. Let fx equals to, let's say, x squared plus 4. Do we have the zeros for this function? Yes. According to fundamental theorem of algebra that you will see later on, this function fx is a function with, is a polynomial with degree of 2. So it should have 2 zeros. It should have 2 zeros. Okay, it should have 2 zeros. How do we do that? Well, set the zeros. How to find the zeros? We set the fx equals to 0 and then solve it, right? Negative 4 equals to x squared. So x squared, so x equals to plus minus square root of negative 4. X equals to plus minus 2i. So x1 is 2i, x2 is negative 2i's. So it has two zeros. Those are the zeros. But because those zeros are not real numbers, right? These are not real numbers. Consequently, no x-intercept. So from here, you see that not all zeros translate into x-intercepts. So never think that zeros the same to x-intercept. No, they are not. They are not. Zeros are the numbers, maybe complex number, such that fx equals to 0. Now, x-intercept has to be a real number, comma 0, so that you can plot that on coordinate system, right? Okay. You cannot say, oh, the x-intercepts are, you cannot say the x-intercept are 2i, comma 0, and then negative 2i, comma 0. No, try to plot that on the coordinate system. It doesn't work. There's no such thing. There's no such coordinates on our coordinate system. Okay, I hope now you realize this is the last time. Again, I emphasize that when I ask you for x-intercept, you need to write that in coordinate. Why? Because there's a big difference between zeros and x-intercepts. Okay, at least from polynomial point of view, the number of zeros always equals to the degree of that polynomial. Okay, this polynomial here is degree of 2, therefore it has 2 zeros. Okay, but notice that we don't have x-intercepts. So to say that the zeros just the same to x-intercept is not true. Okay, it's not. But Thomas, you know what I mean? No, you don't know what you mean. You say something, but you don't realize that. Like you say something until you are until you encounter something not the same to what you said earlier. Then you say exception, except when the zeros are, the zeros are complex numbers. No, you don't change your goal. You don't change what you said earlier. I mean, so you didn't say, if that's not what you mean, that's not what you say. You should not say it that way if that's not what you mean. Okay. The zeros are not the same with x-intercept, therefore should not be written as zeros. Okay. Now let's go back. I spent plenty of time here on this number 13. Let's go on with number 17. Number 17, basically going the same routine again, show that x minus 3 is a factor of fx equals to x to the fourth minus 2x cubed plus 3x minus 36. And to do so, or let me change to blue. Solution, I do the synthetic division. The first row are the coefficients of the polynomial in descending order as always. 1x to the fourth minus 2x cubed plus 0x squared plus 3x minus 36. Okay, notice that I have a placeholder here, right? And then divided by x minus 3. So I put 3 here. Okay, so they ask factor question, I do division. But the division is syntactic division. So the first number 1 falls down, 1 times 3 is 3, negative 2 plus 3 is 1, 1 times 3 again is 3, 0 plus 3 is 3, times 3 is 9, the sum is 12, 12 times 3 is 36, negative 36 plus 36 is 0. Okay, so since f3 equals to 0, then x minus 3 is a factor of fx. In fact, we can say further that, what happened with this? In fact, we can say further that the fx, which is x 1, 2, 3, to the 4th minus 2x cubed plus 3x minus 36, can be factored to be x minus 3 times x cubed plus x squared plus 3x plus 12. So you see this is x minus 3, right? And then this guy here are the coefficients here. Not only I found the fact that x minus 3 is a factor, I can even go further that polynomial fx is x minus 3 times what? Okay, number 21. Number 21. Find a polynomial fx. Find a polynomial fx with leading coefficient 1. So a n equals to 1. With given degrees and zeros. With degree of 3, that's number 21, the degree of 3. The zeros, they give us 3 zeros also, plus, minus, 3, and 1. Okay, now we need to find that polynomial. Okay, the zeros are x equals to 3, x equals to negative 3, x equals to 1. Remember what zeros mean? This means f3 equals to 0. F negative 3 equals to 0. F1 equals to 0. That's what it means. Okay, but now once we get the zeros, then we also get the factors. It means x minus 3 is a factor, x plus 3 is a factor, x minus 1 is a factor. Okay, now it already degree of 3. Degree of 3, it means it has to be x cubed, right? So fx equals to the leading coefficient 1 times those factors, x minus 3, x plus 3, x minus 1. So you see how we build that function back using the zeros. Once you tell me, oh, you know what, the zeros is 3, negative 3, and 1. Can you give me a polynomial that satisfies that zeros? Okay, then if you give me the zeros, implicitly you tell me the factors. If you give me the factors, I just multiply those factors to get the original function. Okay, so I go on further. I will just FOIL this. I get x squared minus 9 times x minus 1. That's x cubed minus x squared minus 9x plus 9. That's the polynomial. Now I'm done. See, in the past, what we did was, like if we get a polynomial, we factor it, right? Right? From after we factor it, we get the zeros. After we get the zeros, we get the X intercepts. Remember? Now we basically reverse the process. They don't tell us the X intercept, they tell us the zeros. Now, using those zeros, we will rebuild the function. Now, the thing is, there are actually a lot of functions with these zeros. Maybe I write it as a note. In general, Px equals to a times x minus 3, x plus 3, x minus 1 gives us is all the polynomial with zeros plus minus 3 and 1. Okay, now in this case, they insist the leading coefficient has to be 1. That's why the function, the polynomial, becomes unique. But giving us the zeros only, does not give us a unique polynomial. Okay, you have the leading coefficient to play with. Okay, so let me modify this question a little bit. Okay, let me modify this question a little bit. Number 21, modified. Okay, modified. Find fx of degree 3, a polynomial with degree 3, with zeros plus minus 3 and 1, and let's say f0 equals to 5. So they don't tell us the leading coefficient has to be 1. In that place, they tell us the y-intercept 0, 5. Now, how to find this function? So the zeros are x equals to 3, x equals to negative 3, x equals to 1. Remember, in the past, I don't want you to just say x equals to 3, negative 3, 1 like that. Okay, I don't want you to write it that way. I don't like you to write it that way, and I have my reason. Okay, that laziness of writing it in precise notion is the one preventing you from going forward precisely. Okay, you're supposed to write the zeros this way. Just spell it out. X equals what, x equals what, x equals what. Now then, from there you get the factors. X minus 3, x plus 3, x minus 1. So the function fx must be a leading coefficient, which we don't know yet, times x minus 3, x plus 3, x minus 1. Now fast forward, if I multiply that polynomial, I will get x cubed minus x squared minus 9x plus 9. Okay, now I need to find the a. I need to find the a. Now what is f0? F0 equals to a times 9 because x equals to 0, right? At the same time, we know that's equals to 5. So a equals to 5 over 9. Now using that, then we get the full function fx equals to 5 over 9 times x cubed minus x squared minus 9x plus 9. Which of course we can distribute that 5 nines to be 5 over 9x cubed minus 5 over 9x squared minus 5x plus 5. Okay, so you see that, yes, we have a lot of polynomials with degree 3s with these zeros. Okay, now one of them with leading coefficient 1. The other one, suppose if I say f0 equals to 5, then you do that adjustment. Okay, that's for number 21. Let's do a couple more questions. Let me see what else I need to. Oh, I'm still at number 21 only. I still have a lot. 25, 29, 31. Okay, number 25. Give me a second. Number 25. Use syntactic division to find the quotient and remainder if the polynomial divided by the second. Number 25, so we have that polynomial. Let me use px. The polynomial px is 2x cubed minus 3x squared plus 4x minus 5 divided by qx, the quotient, the divisor, x minus 2. And that tells us to use syntactic division, which is really nice. Usually, they don't need to tell us that. Okay, just say, they may just say, oh, divide this polynomial by that polynomial. And then you come up to your own idea. Hey, you know what? The divisor is x minus c form. So I can use syntactic division. Only when the divisor is in x minus c form, you can use syntactic division. If the divisor is x squared plus 1, no. If the divisor is 5x squared minus 7, no. Even if the divisor is 2x minus 1, no. It has to be x minus something. It has to be in this form. Okay, then you can use syntactic division. Let me start. The coefficient of the divisor, 2x cubed minus 3x squared plus 4x minus 5 divided by x minus 2. So this is 2, 4, 1, 2, 6, 12, 7. Okay, so the quotient is 2x cubed minus 3x squared plus 4x minus 5 over x minus 2 is equals to 1 degree less 2x squared plus x plus 6 plus 7 over x minus 2. Okay, that's number 25. Number 29. Okay, the polynomial we divide is 3x to the 5th plus 6x squared plus 7 divided by x plus 2. So syntactic division, because the divisor is x minus c, where the c is negative 2. 3x to the 5th plus 0x to the 4th plus 0x cubed plus 6x squared plus 0x plus 7. Okay, notice that we have a lot of placeholders. Be very careful. Now then we will divide. 3 times negative 2 is negative 6. I add that. Negative 6 times negative 2 is 12. I add that. That's negative 2 times 12 is negative 24. That's negative 18. Negative 18 times negative 2 is 36. I add negative 72. This is negative 65. So 3x to the 5th plus 6x squared plus 7 divided by x plus 2. If you try to use long division, it will take you forever to get this. You know, and of course, you will lose too much. It's too much effort such that you lose too much energy in between, and you get tired really fast, and you may complain really early too. Okay. That's number 29. What is next? Number 31, 35. Number 31. So I do a lot more problems in this section. So we want 4x to the 4th minus 5x squared plus 1 over x minus 1/2. So solution. Four x to the 4th plus 0x cubed minus 5x squared plus 0x plus 1 over divided by x minus 1/2. So I put 1/2 here. Okay, and then the 4 comes down. 4 times 1/2 is 2, comes down. When I add is 2. 2 times 1/2 is 1. When I add, I get negative 4. Times negative 1 is negative, times 1/2 is negative 2. I add that. Times negative 2 times 1/2 is negative 1. Oh, the remainder is 0. Nice. Okay, so it means 4x to the 4th minus 5x squared plus 1 over x minus 1/2 is equal to 4x cubed plus 2x squared minus 4x minus 2. Notice that the remainder is 0. Okay, notice that the remainder is 0. So remember that if the remainder is 0, then x minus c, in this case x minus 1/2, is a factor. Okay. In the long run, in in section 3.3 or maybe even 3.4, let me see, 3.3. Yeah, in 3.3 or 3.4, when we try to graph this, polynomial here, when we try to graph that polynomial there, then we will find that it is a 1/2 is a 0, 1/2 comma 0 is an x-intercept. Okay, let me do some follow-up work. Now, since the remainder is 0, so we can write 4x to the 4th minus 5x squared plus 1 as x minus 1/2 times 4x cubed plus 2x squared minus 4x minus 2. Right? And I can go on further. I can factor the 2 out. Right? Because inside the second factor here, you have common factor 2. Okay. And notice that we can factor this further by factorization by grouping. So the first two terms common factor x. The last two terms common factor -1. So we get 2 times x minus 1/2 times 2x plus 1 times x squared minus 1. All of a sudden, we fully factor it. Okay. So if I use this as an example of what we will see in the long run, then once you know that 1/2 is a 0, you can use that 1/2 as a 0. Therefore, it is a factor. And all of a sudden, degree of 4, you factor x minus 1/2 out, you get this guy, degree of 3, which we happen to be able to factor by grouping. And we get the rest of the zeros. Now we get all 4 zeros according to fundamental theorem of algebra. Okay, and getting all 4 zeros enable us to find all x-intercepts, right? Enable us to find all x-intercepts. And notice that these zeros also critical numbers when we do the sine graph. Okay, so let's see. So x-intercepts are 1/2 comma 0, -1/2 comma 0, -1 comma 0, 1 comma 0. Maybe I'm a bit too fast. Let me insert one statement in between. The zeros are x equals 1/2. This is x equals -1/2. This is x equals to -1. X equals to 1. And then from those zeros, all of them real numbers, we get the x-intercept. Meanwhile, we know what's the y-intercept of this function. That's 0, 1. Right? The y-intercept, the x-intercept for this function is this. The y-intercept is 0, 1. Okay, now let's do the sine graph. Using those zeros, we get critical numbers. So the sine graph will be, we have -1, -1/2, 1/2, and 1. The y-intercept is 0, 1, therefore it's positive. All the zeros are multiplicity of 1, so when I jump across the critical number, I change the sign. Jump across critical number, I change the sign. Jump across the critical number, I change the sign. Jump across critical number, I change the sign. So that helps us later on when we graph. Give me a second. When we graph, then the sketch of the graph will be as the following. The x-intercepts are -1, 0, -1/2, 0, 1/2, 0, 1, 0, and y-intercept 0, 1. Okay, and this is degree of 4, right? It's degree of 4. Then it looks like this. That's what the graph looks like. In fact, if you look at this polynomial here, this px here, notice that it is an even function. That's an even function. So p negative x equals to px itself. So it has y-axis symmetry. Okay, it has y-axis symmetry. From the sine graph, you notice that in this interval, it's positive, which means it's above x-axis. From -infinity to -1, -1/2 to 1/2, 1 to infinity, that's above x-axis. That's why the sine graph is positive. And when it is negative sign, it's below x-axis. So you see, all of the sudden, whatever you learn about x-intercept, y-intercept, polynomial, zeros, the sine graph, okay, the even function, suddenly put together in this one question here. Okay, that's why in your test 1 next week, your chapter 1 and chapter 2, I insist on certain way to write things because we need that in chapter 3. Okay, in such details. Otherwise, you will get confused with what, I mean, it is possible even right now, you're already confused with what we learn, right? Okay, and to add to that confusion, you insist, some of you insist not to write it the way I want it. Okay, no wonder later on you get even more confused and you wonder, but Thomas, I'm confused. Well, you confuse yourself to start with by not following what I write you. That's the way I learned it before, Thomas. That's why you are repeating the class. That's why you barely get to pre-calculus, maybe. Okay, there are many reasons. Okay, pre-calculus in itself is tough, and you try to walk away from what I tell you to do, you get even more confused. Okay, how far do you want to go to in your calculus? Some of you need to go to Calc 2 and Calc 3, right? So not only Calc 1. You know, if you barely survive Calc 1, then Calc 2 basically a dream for you, and say bye-bye to your degree. You don't want that to happen, right? You don't want to study something that you cannot use later. Okay, that's why I encourage you to study, to do it the way I do, because at least have faith in me that I usually teach Calculus 2 and Calculus 3. Okay, let me do one more and then we take a break. Number 35. Just a long sections because I do a lot of problems, but you see all of them relies on syntactic division, right? Okay, so when it comes to polynomial, it is impossible to move on without knowing how to use syntactic division. We have fx equals to 0.3 cubed plus 0.4x. Use syntactic division to find f negative 0.2. Use syntactic division to find f negative 0.2. And they actually don't need to tell you use syntactic division. They will say, of this is the function, okay, this is the function, find f negative 0.2. So the polynomial 0.3x cubed, 0x squared, 0.4x plus 0. So you see we have placeholders here. Okay, divided by x plus 0.2. Now let's compute that. 0.3 positive times negative, that's negative. 1 decimal place times 1 decimal place is 2 decimal places. 2 times 3 is 6. Negative 0.2 times negative 0.06. 2 times 6 is 12. 1 times 2 decimal places is 3 decimal places. And negative times negative is positive. So the product is 0.012. When I add, this is 0.412. Multiply by 2, it's 824, but now it is 4 decimal places with negative. So you see, I compute this with our calculator. Okay. By the way, just to remind you how to multiply decimal. Let's say 0.7 times 0.06. How do you multiply it fast? Okay, 7 times 6, 42. 1 decimal place times 2 decimal places give us 3 decimal places. Done. Like that. Okay, you don't need calculator for this. Okay, so you see how I multiplied that 0.412 multiplied by negative 0.2. How did I do that? Right? The way I did it, I multiply 412 times 2. 412 times 2 is 824. How many decimal places in total? 4 decimal places. Positive or negative? That's negative. Done. Okay. By the time you grab your calculator, you have not punched that in yet. I am already done with my multiplication. Okay. Now, of course, you can only do it fast if your preparation in pre-algebra around 2 years ago is sufficient. Okay. Introducing you too early to calculator basically disabled you from knowing this fact. Okay, so please don't think that technology enables us to do more things. No. And technologies at the same time increase our dependence on them. Okay, there are some funny stories that I can tell you because of technology. Some questions. Okay, let's take a little break right now, but at the same time, I would like to share with Oh, I'm sorry. I forgot to unmute myself. Thank you. Yeah. Yes. Well, that's basically it. Number 39, right? And then we divide by. Yeah. Thank you. Okay. We divide by x minus 2 plus radical 3. So the polynomial, I write the coefficients here, right? And then divide by 2 plus radical 3. We have that here. Okay, now then just like before, the first number falls down, and then I multiply by that, give me this. Okay, and then after that, I get that 2 plus radical 3, I add. When I add, I get 3 plus 2, I get 5 plus radical 3 by itself. So now I need to multiply 2 plus radical 3 times 5 plus radical 3. 1, 3, negative. Oh, thank you. So this negative 5 here. Negative 5 here. Okay. Now then, when I FOIL this, I get 10 plus 2 radical 3 plus 5 radical 3 plus 3. We get 13 plus 7 radical 3. 13 plus 7 radical 3. So the sum will be 8 plus 7 radical 3. So f2 plus radical 3 is being done the same way we did that before. Okay. That's for number 39. Number 41, similar to what we have done before. Number 41. Use syntactic division to show that C is a zero of fx. Number 41, fx is 3x to the 4th plus 8x cubed minus 2x squared minus 10x plus 4. And we want to show that C equals to negative 2 is a 0. Is give me a second. I don't know what happened with my note. Is 0. Now, but that implies f negative 2 equals to 0, right? Now, to show that f negative 2 is a 0, what we can do is to show the remainder is 0. Solution. Okay, 3x to the 4th, 8x cubed minus 2x squared minus 10x plus 4. Negative 2 is a 0, so you put negative 2 there and you try to show that the remainder here is 0. Okay, so 3, negative 6, 2, negative 4. Negative 6 times negative 2 is 12. This is 2 times negative 2 is negative 4. Negative 4 plus negative 4 is 0. Okay, so by remainder theorem, f negative 2 equals to 0. Negative 2 is 0 of that fx. Okay, that's for number 41. Number 45. Number 45, find all k's such that fx is divisible by the given linear polynomial. We have fx equals to kx cubed plus x squared plus k squared x plus 3k squared plus 11 That's the polynomial. Okay, fx is divisible. Hold on, give me a second. Fx is divisible by since yesterday. I don't know what's wrong with my computer. Since yesterday. Yesterday is worse though. If you watch the recording from yesterday, it was I don't know. It's just so bad. Okay. Apparently, Windows have their updates, and that updates slows down a lot of computer. I thought it's my computer. I mean, it is my computer, but it's because of the Windows updates and a lot of programs at SMC's computer also not working well. They need to sign out, sign in, and reverse the update. Well, anyway, so if fx is divisible by x plus 2, fx is divisible by x plus 2, implies, means x plus 2 is a factor. Is that right? But if x plus 2 is a factor of fx, means negative 2 is a 0. Which means f negative 2 is equal to 0. You see? Okay, f negative 2 is equals to 0. So that implies f negative 2 equals to k times negative 2 cubed plus negative 2 squared plus k squared times negative 2 plus 3k squared plus 11, and that is equals to 0. Let's simplify. This is negative k squared minus 8k. So it's behaving again. Minus 8k plus 15 equals to 0. Factor the negative, divide by negative 1, both sides. Am I making any mistake somewhere? Give me a second. So this gives me negative k 3k squared, the second line. Oh yeah, thank you. This is 3k squared. So this is positive k squared then. I don't need to divide by negative 1. So from there we get k minus 3, k minus 5. So k should be 3, k should be 5. Okay, so for this polynomial, going back, for this polynomial to be divisible by x plus 2, the k needs to be either 3 or 5. Okay. That's for number 45, the last one, more into theoretical. Last one, number 51. Number 51, proof that x minus y is a factor of x to the n minus y to the n for every n. To be more precise, n positive integer. How do we prove that statement? We define a function first, define a polynomial. Let px be x to the n minus y to the n. Okay, if x minus y is a factor, to show that it is a factor of x to the n minus y to the n, then y is a 0 of that px, right? Then py equals to 0. Okay, so that's the idea. That's what we will do. So, to show that x minus y is a factor, I need to show that y is a 0. That's x minus c, right? Y is a 0. It means I need to show that py equals to 0. Okay, now let's redo this. At least we get the idea already. Oh, we will do it that way. We'll do it that way. So px equals to that. Now py, therefore, is y to the n minus y to the n. That's 0. Okay, so y is a 0 of px, and by factor theorem, x minus y is a factor of px. That is x minus y is a factor of x to the n minus y to the n. Okay, now because before I finish up with this section, that's the last question I want to do in this section, but I want to tell you even further. It's basically say the following. Okay, x minus c is a factor of x to the n minus c to the n. Okay, now if it is a factor, then we must be able to define that, right? Okay, suppose, for example, we use n equals to 5. Let n equals to 5. Okay, so I want to factor x to the n minus c to the x to the 5th minus c to the 5th. That's equals to x minus c times what? Okay, so basically x to the 5th minus c to the 5th over x minus c equals to what? Okay. How do we factor it? How do we factor it? So let's change that c for the purpose of simplicity. Let c equals to choose a number. Let c be 3. Okay, so we want to know what is x to the fifth minus 3 to the fifth divided by x minus 3. Okay, we want to find that out. Okay, using syntactic division, 1x to the fifth, 0x to the fourth, 0x cubed, 0x squared, 0x 3 to the fifth. And this is 3 here. So 1 down times 3. This is 3. This is 9. This is 9. 27. 27. 81. 81. This is 243, which is 3 to the fifth. Oh, this should be minus here. Okay, so x to the fifth minus 3 to the fifth over x minus 3 is equal to x minus x to the fourth plus 3x cubed plus 9x squared plus 27x plus 81. Okay, now if we leave that c as c instead of changing it to 3, okay, x to the fifth minus c to the fifth over x minus c equals to what? The syntactic division will be, this is c, 1, 0, 0, 0, 0, negative c to the fifth. So I change it back to c instead of a specific 3. So 1 times c is c, this is c squared, this is c cubed, this is c to the fourth, this is c to the fifth. Okay, now all of the sudden we get this x to the fifth minus c to the fifth equals to x minus c times x to the fourth plus cx cubed plus c squared x squared plus c cubed x plus c to the fourth. We already factor it. Now the thing is, it applies for every positive integer n. Okay, now so one of the specific case that you may forget is how do we factor x cubed minus y cubed? How do we factor that? Now we know that x minus y must be a factor, right? X minus y times what? Then you can play with syntactic division. Okay, 1x cubed minus 0x squared minus 0x minus y cubed. And you put y here. Okay, so 1 times y is y, 0 plus y is y, this is y squared, this is y squared, this is y cubed, this is 0. So from there we see x cubed minus y cubed equals to x minus y times 1x squared plus xy plus y squared. Okay, just in case you forget how to factor difference of cubes. Okay, that's for 3.2. Let's go to 3.1. 3.1, number 5. Use intermediate value theorem to show that f has a 0 between a and b. Okay, let fx equals to x cubed minus 4x squared plus 3x minus 2. And the question is there any zero between x equals to 3 and x equals to 4? We will use intermediate value theorem. Okay, we will use intermediate value theorem. Okay, we will need to find what is F3, and we need to find what is F4. Okay, now to find F3, one thing you can do, you plug in 3 into that functions, or you can use synthetic division. 1, -4, 3, -2, this is 3. So F3 is -2. How about F4? So instead of plugging x equals to 4 into that function, I rather just use synthetic division. It's faster. Okay, so F4 is 14. Now notice that what happened then, what happened then if we look at the number line, right? When x equals to 3, the outcome is negative number, right? When x equals to 4, the outcome is positive 14. Now, because they have different sign, then there must be a critical number in between. Right? There must be a critical number in between. And on the top of that, we know polynomial should be continuous. Therefore, it's the critical number is not the undefined case. What did I do? Oh, it's -2. It's -2 here. I copied that wrong. So it should be 10. Should be 10. It's still positive. Okay, so we have a critical number here. Okay, and because polynomial never undefined, okay, then it must be 0. Okay, does it make sense? Okay, what we did before is this: if we have critical numbers, let's say 5, okay, and then we see that we may have opposite signs. For example, negative, positive, right? Okay, now we reverse the ordering. If you see that on the left-hand side is negative sign, on the right-hand side is positive sign, then there must be a critical number in between. Okay, the critical number either make it undefined or 0, but we know polynomial has domain all real numbers, right? So it won't be undefined, it must be a 0. Now, intermediate value theorem says that if FA and FB, in this case 3 and 4, have opposite sign, one of them positive, the other one negative, then for sure there is a 0 in between. Okay, by intermediate value theorem, there is a 0 between x equals to 3 and x equals to 4. In other words, we have an x intercept between 3 and 4. We have an x intercept between 3 and 4. Okay, now intermediate value theorem only tells us the existence. It doesn't tell us what is. It only tells us that there's a 0, but it doesn't tell us what is the 0. Okay, it only tells us there is a 0 between this guy and that guy. Okay, but what is the 0? We don't know. Okay, now this intermediate value theorem later on you see becomes quite crucial in 3.3. Next question, number 9. similar questions, I believe. We have fx equals to x to the fifth plus x cubed minus 3x plus 1. Is there any zeros between in that interval -2 to -1? That's just another way to ask that. In this interval -2 to -1, is there any zero there? Is there any x-intercept between -2 and -1? So we compute what is f -2 and what is f -1 later on. Okay, 1x to the fifth, 0x to the fourth, 1x cubed, 0x squared, -3x plus 1. -2 here. -33. We just care that it is negative. Okay, and how about f1? F -1. Remember, we just need them to be opposite signs. So we don't really need the -33 actually. Okay. 0, 1, 0, -3, 1, 1 falls down. So f -1 is positive number. Okay, it's a positive number. Okay, so by intermediate value theorem, there is a zero in that interval -2, -1. Okay, now I will do number 11, but we are required to look at the textbook. So please take a look on your textbook for number 11. Let's see the textbook for number 11. Let's see the graph first. 11a. Should I give me a second then? Let me screenshot. Do I have the book here in this? I don't think so. Well, anyway, so 11a. The graph looks like as the following. It looks like this. It has x-intercept -1, y-intercept +2 approximately, and then x-intercept 1, 0, 2, 0. So it looks like this. Okay, so what can we say about this? Well, the zeros are the x-intercepts, as we can see here, are I'm sorry, -1, 0, 1, 0, 2, 0. Okay, so the zeros are x equals to -1, x equals to 1, x equals to 2. And you see that it crossed the x-intercepts just like that, like when it cross, it's not behaving strangely like this. You know, it's not doing that. It's just crossed that like that. It just crossed that like that. Not curvy when it intersect the x-axis. Now, if that's the case, it means those are zeros with multiplicity of 1. It cross linearly. Okay. Now, therefore, if it is zeros with multiplicity of 1, then the factors will be just also multiplicity of 1, x plus 1, x minus 1, x minus 2. Okay. So the function fx must be something times x plus 1, x minus 1, x minus 2. Now then, how do I find the a? Now notice that the y-intercept is 0, 2. Which means when x equals to 0, the y is 2. Okay, so 2a equals to 2a equals to 1. So we now recover the function from the graph. Fx equals to 1 times x plus 1, x minus 1, x minus 2. Now compare that with the graph of part B. The graph of part B looks like the following. The x-intercept are -1, 0, 1, 0, and 2, 0. However, it works, it looks like this. Okay, so what happened here? What happened here? You see, the left-hand side, if you look at the sine graph, right? 1. On the left-hand side is negative. This is 0. It's negative. There's no change of sign. There's no change of sign at critical number x equals to 1. Okay, because there's no change of sign, then 1 is a 0 with even exponent, even multiplicity. Multiplicity. From the x-intercepts, we see that x-intercepts are -1, 0, 1, 0, 2, 0, which means the zeros are x equals to -1, x equals to 1 with multiplicity even, x equals to 2, which means the factors are, x plus 1, x minus 1 to power even exponent, and x minus 2. Okay, so fx is equal to leading coefficient a times x plus 1 times x minus 1 to the even power, and x minus 2. Okay, so we cannot go on further from there, but at least from the options we see, this is option D. That's the only one have that pattern. Let's do one more. The third graph. Part C. We have x-intercept 0, 0, which is also the y-intercept, and 2, 0. The graph looks like this. So from there, we see the X intercept is 0, 0 and 2, 0. In fact, the zeros are Cx equals to 0 is a 0 with multiplicity even. Why? It's bouncing. To the left and to the right, it has the same sign, both positive. Right? If we zoom that in, X equals to 0 is a 0, and on the left-hand side, the graph is above x-axis, the right-hand side also above x-axis. So it must be multiplicity, it must be even multiplicity. Is x minus 2. So the factors must be x to the even power and x minus 2. So the polynomial fx must be a times x to even power times x minus 2. Okay, and the one that satisfies that pattern is equation or function b. Okay, you can also do this one. To detect if A is positive or negative, you can take a look here. Let's say F3, right? F3 should be negative, right? F3 should be negative. So if I plug in F3, that's A times 3 to even power times 3 minus 2. It should be positive, right? But this is A times positive times 1 positive. Hold on. Negative, not positive. I quote it wrong. Yeah, F3 is negative. So this should be negative here. Should be negative. This is negative. Yeah, then A is negative. Okay, that's why we can say further that it must be function B. Let's go on further. I have 10 minutes left. That's number 11, number 13. The far end behavior. Let me do it here. Number 13, far ends behavior. (13a) fx equals to 3x to the 5th minus 2x cubed plus 6. How will the graph of this function behave when x goes to infinity and when x goes to negative infinity? It follows the leading term only. Okay, and far ends behavior is basically you need to memorize. Even though you can also work on that if you want. For example, as x goes to infinity, what will happen to fx? Okay, now when it comes to polynomial, the dominant term is the leading term. When x becomes very, very large, the contribution of the remaining terms becomes very not significant. You only look at the leading term. Now then, when x goes to infinity, what happened to the value of that leading term? That will tell us the value of the overall polynomial. When x goes to infinity, 3x to the 5th will go to infinity. How about as x goes to negative infinity? You plug in negative infinity, very big negative number there. On the leading term, you get negative infinity. In other words, when we go very, very far to the right, when we go very, very far to the right, the graph will go to positive infinity. When we go very far to the left, it will go to negative infinity. Okay, the shape of the graph will be approximately looks like this. Which means when you go very far to the right, the value of the function goes to positive infinity. When you go very far to the left, it goes to negative infinity. Okay, so far end behavior is actually quite simple. Okay, you just look at the leading term. Okay, you just look at the leading term and imagine if you plug in infinity to that leading term, imagine if you plug in negative infinity to that leading term. Now, what happens if we have part C instead? So fx equals to 2x to the 6 plus 5x squared minus 3x. As x goes to positive infinity, what happened to the function fx? Again, the dominant term will be the leading term. So to know how the function behaves when you go very far to the right, just look at the leading term. When x goes to infinity, then the leading term will also approach infinity, while as x going to negative infinity, fx, the leading term, will still go to positive infinity. Okay. In other words, when you go very far to the left, it goes to a positive infinity. When you go very far to the right, it goes to positive infinity. We don't know what happened in between. That's for number 13. Number 17. Find all values of x such that fx is positive and when fx is negative. Basically, we will do sine graph. We will do sine graph. Okay. Now, instead of doing the inequality, remember step 1, 2, 3, which you have to do in step 1, 2, 3 in your test 1. Okay. I said that when I go over the test, so make sure you take a look when I take a look with the solutions I gave in Monday, Wednesday class when I went over test 1. Okay. But basically what I need to do here is using that procedure, three-step procedure, but only go up to step 2. Step 1, critical numbers. Set this function equals to 0. Multiply by the LCD negative 16. I get 0 equals to x to the 4th minus 16. I can factor this, x squared plus 4, x squared minus 4. I can factor further, x squared plus 4, x plus 2, x minus 2. So the zeros are, the critical numbers are negative 2 and positive 2. Then I do the sine graph. When x equals to negative 2, it gives me 0. When x is positive 2, it gives me 0. Now, plug that into the original function. Plug that into the original function. For example, when x equals to 0, the y is positive 1, right? And you can see from the factoring, negative 2 and 2 are zeros with odd multiplicity, which means when I jump across those critical numbers, I change the sign. Then we are actually done. We just need to do the conclusion. Okay, so fx is positive on what interval? On the interval -2 to 2. Notice that it's strictly positive, right? So I don't include the endpoints that give us 0. Now fx is negative on the interval -infinity up to -2 union 2 to infinity. Okay, this is the place where it is positive. That's the place where it is negative. Okay. Let me see, you have question coming in. Can you answer that? Do we have a class on this Thursday? Do we have a class this Thursday? As I know, yes. Yes, we have class this Thursday. May I know why you asked that question? I may not be aware of some informations. I heard that all class is rest because of holiday. Let me check first then. Okay, give me a second. Give me a second. I know there's one day they say it's a flex day, but I thought it's actually next week. Not, I thought it's the 25th, but it happened to be the test day. But give me a second. Let me check first. So I just find out that on this Thursday, March the 18th, we will have a day off. It's department flex day. So we will continue on 3.1, 3.3 on March the 23rd.